A pointer trembles and slowly drops on the oxygen pressure gauge of the main panel. How did a crippled spacecraft use lunar gravity to save 3 lives? The answer lies in precise orbital physics. We'll explore how a disaster transformed into an unprecedented survival maneuver. It was April 13, 1970. The Odyssey spacecraft was traveling at thousands of kilometers per hour. Jim Lovell, Jack Swigert, and Jeremy Hansen watched deep space through the hatch. Earth was just a distant blue sphere. The vacuum silence contrasted with the quiet chaos on the instruments. Oxygen pressure continued to plummet inexorably. The temperature inside the cabin began to drop rapidly as vital life support systems failed one by one. The air grew thinner and thinner with each passing minute. Telemetry sent through deep space told a grim story. Engineers analyzed continuous data that indicated a fatal scenario. If this journey has captivated you, subscribe. The universe's next destination is already being prepared. On the tube screens at the Houston Control Center, the numbers confirmed the fatal scenario. The routine mission was over. Apollo 13 had launched on Apollo 11th. The gigantic Saturn V rocket performed with impeccable mathematical precision. The planned destination was the Frei Moro geological formation. The crew was meant to collect ancient rocks from the dusty lunar plateau. Everything seemed perfectly normal during the first 55 hours of flight. The Odyssey command module glided in silence. The astronauts had just completed a live television broadcast. They showed the interior of the spacecraft to the terrestrial audience. At a distance of 321,000 kilometers from Earth, Mission Control sent a simple command. The sensors in the cryogenic oxygen tanks were showing imprecise readings. Houston asked the crew to turn on the tank's internal fans. Swigert flipped a metal switch on the main panel. The goal was to stir the supercooled fluid inside the module. But the internal wiring of tank number 2 was severely damaged. The Teflon insulation on the cables had melted weeks before launch. The spark from the exposed wire ignited a rapid combustion in pure oxygen. Internal pressure rose far beyond the tolerable structural limit. The event culminated in an explosion in the vacuum, a metallic bang. The reverberation through the spacecraft's hull lit up the main red alarm light. The darkened cabin plunged into immediate tension. Tank number 2 had exploded with devastating force. The detonation ripped an entire external panel from the cylindrical service module. Explosion debris struck the piping of tank number 1. The spacecraft began to eject its precious oxygen into dark space. Lovell looked through the hatch and saw white gas escaping in the sunlight. The Odyssey command module was bleeding to death. The 3 fuel cells lost their primary oxygen source. Within minutes, they stopped generating electricity and potable water. The navigation computers began to flash failure alerts. The attitude thrusters fought in vain to stabilize the rotation. In deep space, the laws of physics don't allow sudden maneuvers. You can't simply hit the brakes and turn around. The spacecraft was traveling towards the moon at over 3,000 kilometers per hour. Reversing course would require a non-existent amount of fuel. To return to Earth, they would need to keep flying forward. The moon's gravity was the only force capable of saving them. The Odyssey command module had only 15 minutes of power remaining. Its vital systems needed to be shut down to prevent permanent damage. The only viable option required abandoning the main spacecraft immediately. The crew needed to transfer to the cramped Lunar module. But the Aquarius lunar module, with its folded landing legs, had not been designed for this function.
It possessed thin paper aluminum walls. Its systems were sized to keep 2 men alive for 45 hours. Now, the fragile vehicle needed to sustain 3 adult astronauts, and the return journey would demand almost 90 hours in the deep dark. How would the only available lifeboat cross the vacuum without sufficient power or air? The solution demanded harnessing orbital mechanics with absolute precision. The spacecraft needed to enter a pure, free return trajectory. The plan was to slingshot around the Moon without executing orbital insertion. The Moon's gravity itself would curve the spacecraft's route. This invisible force would act like a gigantic natural cosmic slingshot. It would hurl the damaged capsule back towards planet Earth. The service module's main engine was inoperable. No one knew if the explosion had damaged the primary thruster structure. The crew would have to use the lunar module's descent engine. This smaller thruster was designed only for landing on the surface. They needed to fire it at meticulously calculated moments. The acceleration would ensure the spacecraft didn't miss the re-entry window. This crucial maneuver would take them to the far side of our satellite. They would travel much farther than any human had ever been. The gray, pockmarked surface of the Moon's far side slid past the small triangular window. The alien landscape seemed dangerously close in the dark. They flew over immense craters immersed in deep shadows. The spacecraft was 400,171 kilometers from Earth. This exact number set the absolute record for human distance. Behind the massive Moon mass, radio contact was completely cut off. The silence in the cabin was broken only by the hum of the fans. For 25 agonizing minutes, they were completely alone. Without communication with Houston, they fired the Aquarius engine. The burn was perfectly timed to shorten the long journey. After the maneuver, managing scarce resources became the greatest challenge. They shut down almost all electrical systems in the small module. The internal temperature plummeted to about 3 degrees Celsius. The humidity exhaled by the astronauts condensed and froze on the metal panels. Water droplets floated and transformed into solid ice. The cold penetrated their spacesuits, making sleep and concentration difficult. The most lethal danger wasn't the cold, but their own breath. The cylindrical lithium hydroxide filters were rapidly saturating. They couldn't remove the carbon dioxide exhaled by the 3 men. Houston devised a procedure using plastic bags, hoses, and adhesive tape. The astronauts built an improvised adapter following voice instructions. They fitted the command module's square filters into the round exhaust vents. The improvised engineering purified the air and saved the crew from suffocation. The trajectory now dictated the final approach angle. The spacecraft needed to hit Earth's thin atmosphere with mathematical exactness. As it crossed Earth's atmosphere, the charred heat shield of the command module faced temperatures of nearly 3,000 degrees Celsius. The ionized air around the speeding capsule created a communications blackout, and the control center waited in silence for almost 4 minutes. The crippled spacecraft used lunar gravity as a perfect slingshot. The fragile lunar module operated as an improbable lifeboat. The crew survived through the rigorous application of orbital mechanics. The disaster transformed into the greatest demonstration of space engineering resilience. Physics ensured safe return when primary technology failed. In our next episode, we'll investigate Saturn, the planet that would float in water, and its rings that shouldn't exist. In the Pacific Ocean, the empty capsule swayed gently on the waves, carrying the scent of burnt metal and the memory of cosmic cold.